We've had a bit of a chat about it previously, but let's look at this idea of integration with substitution in a little bit more detail. What the basic idea is, you're trying to reduce the integral into something that's standard, something we're used to seeing. Okay, so a standard integral. So we used to get a wonderful table of integrals on the end of the HSC, but it was the only formulas they gave you. It was just these standard integrals. The ones that you used to get were the simple polynomials. Okay, add 1 to the power over the power. Then the log one. And you'll notice they tend to define things precisely. So they said, oh, that's where x is greater than 0. Because remember, technically, integral of 1 on x dx is the log of the absolute value of x. Then our exponential for a linear function, they gave that one. And the trig one, so there's cosine, sine, and sec squared. The next one they gave, which is probably begins being useful in extension 2 when we looked at conics, if you want to differentiate the parameters. And so that's telling me that because remember, whilst it's a standard integral, you can read them backwards and they become standard derivatives, but it's telling me the derivative of sec is sec tan. Then we had inverse trig, so there's inverse tan, and there's inverse sine. Now they quote it as inverse sine, but remember it could be minus the inverse cos. And then there's these ones, and these are specifically for Fourier integration. So 1 on the square root of x squared minus a squared, and 1 on the square root of x squared plus a squared. And you'll notice they're very similar integrals. The only thing that changes is the sign under the square root sign, which matches the sign under the square root sign in the actual integral itself. So those are the ones we used to get. What we now get, so they give us a whole resource sheet which has got a whole list of different formulas in, but hidden in there are some integrals. They're not all jumped together. So in maths, they've, instead of just doing the polynomial add 1 to the power over the power, they've actually done a full linear function to a power, but it's still that idea of add 1 to the power over the power, but reminding us multiply by the coefficient of a as well in that situation. So the basic polynomial one is not there. Exponential of a linear function, so that's still there. They actually write the log one now as derivative on function. So rather than just limiting it to 1 on x, and they have got the absolute value there on that one. So log of the absolute value of function x. Sine of a linear function, cosine of a linear function, sec squared of a linear function. So they're all there. Then, on the sheet that has the extension 1 stuff, we find the inverse trig ones, but that's it. So missing from the old standard integral sheet was not the sec tan, that's not there anymore, and those last two that I just showed you, the square root of a squared plus x squared, the square root of a squared minus x squared, which is unfortunate. So no longer there, the sec tan and those ones. Certainly ones we need to know though. Then there's what I call the non-standard integrals, ones that's come up a lot and they're just worth knowing to save yourself time. And so things like that. If you see du on the square root of u, I know that's going to be 2 times the square root of u. It's a very common substitution we have where we just end up with the square root of u on the bottom. So that becomes just 2 root u. Another one we see a lot is when it's just u squared on the bottom. That would be minus 1 on u. Log, integrate log, turns out to be x log x minus x. Tan is the log of sec. And this idea, I briefly mentioned it the other day, if you integrate a complementary trig ratio, the answer will be the complement of the answer. What do I mean by that? Okay, if I want to find the integral of cot, well, the integral of tan is the log of sec. Right, we know that one. Therefore, the integral of the complementary ratio cot must be minus the complement of the answer. So it'll become minus the log of cosec x. So the trig ratio turns into its complement and a negative goes out the front. So integral of cot minus the log of cosec. That pattern appears all the time. In fact, we've seen it already because remember the integral of cosine was sine. But the integral of sine, which is the complement of cosine, was minus cos, the complement of sine. Okay, well you might prefer to write minus log of cosec as log of sine if you don't like the negatives out the front. That's just a matter of preference, I suppose. Alright, so we've got x times the square root of x squared plus 4. We want to try and turn this into a standard integral. We do it via substitution. What to do for the substitution? Now, in extension 1, they're likely to give you the substitution until you use this one. And so, okay. And that's because in extension 1, I guess they're interested in knowing that you know how to use the technique. And so they're forcing your hand. Whereas in extension 2, sometimes they'll do that, but a lot of the time they just leave it up to you, however you want to do it. So, when I'm going to substitute, what's causing me the problem? I think what's causing me the problem is under the square root sign. So I'm going to go u is equal to x squared plus 4. Now, if u is equal to x squared plus 4, there's the x squared plus 4, so I've got u. Okay. The derivative du, or du dx, would be 2x. So now I've also got to replace, because I can't integrate u with respect to x. I have to have it with respect to u. So I know that I can substitute du in for 2x dx. Well, I've got 1x dx there. Okay. So I've got half of du. So it comes down to now just be half the integral of u to the power of half. I've now got a standard integral. It's a polynomial type where we add 1 to the power over the power. So I get a half of 2/3 u to the 3 on 2. Of course, I don't leave the answer with u in it. That's something I introduced. Got to substitute back in. And there we go. So 1/3 of x squared plus 4 to the 3 on 2 plus a constant. That's the mere mortal answer. And the final answer, I think, looks much nicer. X squared plus 4 root x squared plus 4. Okay, another way of approaching that. See, if a root of a sum or a difference of squares is involved, you could try a trig substitution. And because trig allows you, when you got a sum or a difference of two squares, to turn two terms into one term via a trig identity. Now, I'm not suggesting this is the way I would do this. I'm just showing you it would work. So I'm going to say, well, if I make x equals 2 tan theta, then dx would be 2 sec squared theta to theta. Now I just substitute straight in for x and dx. Now when we do that, sub in, I get 2 tan theta times the square root of 4 tan squared plus 4, and then times the dx, which is 2 sec squared, I get 8 times the integral of tan theta sec cubed, which I can rewrite as sine theta on cos to the power of 4. And then I can do another substitution. I can say, well, let u equal cos theta, so du is minus sine theta to theta, and it becomes minus 8 du on u to the power of 4. Well, that's just u to the power of negative 4. Add 1 to the power over the power, and I've got my answer. I now just have to work my way back and get the x's into it. So substitute in for u. Now substitute in for sec theta. Oh, hang on. X is equal to 2 tan theta. So if I draw myself up a little triangle, so tan theta is x on 2. Pythagoras tells me the hypotenuse is the square root of x squared plus 4, which happens to be the original surd, you'll notice. Not a coincidence. So sec theta I can now read off that as to be 2 over the square root of x squared plus 4, substitute it back in, and we now have the same answer. As I say, I am not suggesting you would use that substitution for this, But it does show you that there are alternative ways of approaching problems. So that idea of trig substitution, we'll see more of those in extension 2, I think, where it is a useful technique. Mind you, if they don't tell you a substitution to use, don't forget about that basic idea. This is one where I could simply have said, oh, let's create the derivative times the function. Because the function is x squared plus 4, the derivative of that is 2x. I've got x out the front, so I could have just multiplied the whole thing by 2, brought a half out the front, add 1 to the power over the power, bang, got it. So don't forget about those ideas as well. Alright, let's have a look at this one. X plus 1 on 4x squared plus 8x minus 7. Polynomial, it doesn't divide. So I'm going to go for the bottom of the fraction. Now what sent me that direction? When I see the order of the polynomial on the top is 1 less than the order on the bottom. Because now I might have a log situation. Because remember, when you differentiate a polynomial, you subtract 1 off the power. So if I notice that difference of 1, it may end up being a log function. So I'm going to make u equal the bottom of the fraction. Let's see what happens. And in this case, it's quite nice because you'll notice it's just a multiple of x plus 1. I can multiply by 8. So I've got 1/8 of du on u, standard integral. So that's log u. Substitute the u back in. There's our answer. Dx on x log x all cubed. Well, the log x is cubed. That's probably a good clue as to what to try for a substitution. So I'll go u equals log x. So du is dx on x, and I've got that bit as well. So that works out quite nicely. So I can change that to du on u cubed, which is u to the negative 3. Add 1 to the power over the power. Sub the u back in. And there we go, minus 1 on 2 log x all squared. X over the square root of 1 minus x. Boy, what to try with this one? If I make u equal 1 on x, that's what's under the square root sign. I suppose I could do that. What did I do? Yeah, so I've done u equals the square root of 1 minus x. But I've actually rearranged it and made x the subject. Sometimes that makes the substitution nicer, because then you can substitute straight in for the x and the dx. So yes, it is u equals the square root of 1 minus x, but I'm thinking about it as x equals 1 minus u squared, and then dx then would be minus 2u du. Subbing in 1 minus u squared on u times minus 2u du. Tidying up a nice neat little polynomial. Add 1 to the power over the power. Substitute the u back in. Well, that's probably good enough for an answer. But hey, let's play. Let's make the square root of 1 minus x all cubed. 1 minus x root 1 minus x. I suppose you could take out a common factor now of root 1. Oh, you could go for your life. You could have all sorts of fun. Yeah. Let's do a definite integral. What do we have to do here? Now, again, if they tell me to do this via a substitution, I'm going to cry. Because look, cos is the derivative of sine. I've got it already as function to the power of 5. I know it's just going to be add 1 to the power over the power. But they'll probably do something like say, oh, use the substitute u equals sine x. And I'm like, why? I could do it just this way, but okay. If u is sine x, the u is cos x. But I've got to change the limits. Because those limits are when the integral refers to x. So what would they be when I do the substitution? Change them to u. Well, the pi on 3, and there's my formula, u equals sine x. That becomes u equals root 3 on 2. Pi on 2 becomes u equals 1. So let's sub it all in. And there's our little integral. From root 3 on 2 to 1 of u to the power of 5. Add 1 to the power over the power. Substitute in, and we have our answer. So notice for this one, there's no need to substitute back because I've changed my limits, and so I can substrate back in. X dx on the square root of 25 minus x squared. Let's see. Well, x is a derivative of x squared. Well, 2x would be. So maybe I do 25 minus x squared. We've got a difference of two squares there, you'll notice. 25 minus x squared. Maybe a trig substitution could be handy for this one. Which way did I go? I've gone for the 25 minus x squared. So du is going to be minus 2x dx. Change those limits. So when x equals 3, u 16, x equals 4, u equals 9. So substituting in, we get minus a half from 16 to 9. But you'll notice in the second line I've swapped the limits around and got rid of the negative sign out the front. Remember, you can always swap your limits on an integral sign. You just got to change the sign out the front. That, if you haven't recognised it, is 1 on root u. Well, that's one of the ones I said, gee, this comes up a lot. So I actually know the answer is going to be 2 root u. But let's prove it. Add 1 to the power over the power. Oh, what do you know? Add 1 to the power of minus a half, you get power of a half. Times it by the half by the 2, we got 1. There we are. Root 16 minus root 9 is 1. Square root of 25 minus x squared. Ooh. Can't do a u equals 25 minus x squared this time because I haven't got an x dx there to play with. So maybe I will do a trig substitution for this one. So if I let x equal 5 sine u, because I've got a difference of two squares there. Okay. So u equals inverse sine of x on 5 basically is the substitution I'm doing. But I'm making x the subject. Makes life a little bit easier for this one. So dx is 5 cos u du. Play with those limits. When x equals 0, u equals 0. X equals 5, u is pi on 2. Substitute in. So we've got square root of 25 minus 25 sine squared. But of course, 25 minus 25 sine squared becomes 25 cos squared. I've got two terms turned into one. But now I can find the square root of 25 cos squared. That's just 5 cos u. So now I've got 25 times the integral of cos squared u. Cos squared, that's where we use one of our double angle theorems. Cos squared we can rewrite as a half of 1 plus cos 2u. And remember, sine squared is a half of 1 minus cos 2u. The handy ones to remember. So now we integrate the 1, we integrate the cos 2u. I get u plus a half sine 2u. Substitute in 25 pi on 4. Now you go, hang on, Mr. Simmons, that's the same question. Yes, you're right. Because it's another one of those ones where if they give me the substitution, I'm going to cry. Because look at this. Square root of 25 minus x squared. Oh, that's a semicircle. I want to go from 0 to 5. Oh, that's just a quarter of the circle. Quarter pi r squared, 25 pi on 4. Thank you. That is how I should be doing it, not via this stupid substitution that they've asked me to use. So hopefully it's a question where they don't ask you to use a substitution and you notice it. Remember, if it's a shape you recognise, use the formula you already know. It's going to be quicker than integrating. Oh, an algebraic manipulation. What's this one? Integral of x cubed, the square root of 4 minus x squared dx. Alright, I'm going to rewrite that. Have a look at it closely, what I've done. You'll notice the x cubed, it's there, minus x times minus x squared. But I've turned the x cubed, if you like, into minus 4x plus 4x cubed. That 4 minus x squared is matching what's under the square root sign. But then if I subtract 4x, I've got to add 4x. Now, apart from you now thinking, he's just gone crazy, what the heck, why on earth would you do this? Huh? But now, look at the two integrals. If I separate them, I've got minus x, 4 minus x squared to the 3 on 2, plus 4x. What we've basically got is a situation where we've now got derivative times the function to the power. Because the derivative of x squared is 2x. And so I've got it there and I can just add one. So sometimes just manipulating the algebra can come in handy. Alright, lots of fun ahead of us.